I'm here to talk about Academy, which is our solution for building agentic scientific workflows across federated research infrastructure. And on this slide, I used to have the ever-growing list of collaborators. I'm really just one member of a large team that's working on this. I have moved that to the end because it was getting unwieldy, but I will try and give credit where credit is due. But no, this is much more than just my work. So just to start out with the lay of the land, what we're talking about when we're talking about building scientific workflows is that we have this ecosystem of diverse, heterogeneous, distributed, federated resources from computing clusters, cloud, sensors, whatever, computing resources, experimental facilities, telescopes, microscopes, self-driving labs, data storages from these experimental facilities, troves and troves of experimental results, literature from arXiv and PubMed and everything. We have all of this ecosystem of scientific resources that we want to take advantage of. We want to build workflows across. And with the increasing strength and prevalence of machine learning methods, LLMs, we want to make these agentic workflows. We want to enable more automated reasoning, more automated control of these facilities to really automate that inner loop of discovery so that scientists can think about higher level directions of where resources need to be invested in hypothesis, and the inner loops get automated by agents. So part of what I want to do is I want to convince you guys that thinking about scientific workflows in this agentic manner is powerful. And then once we're there, I also want to show that in order to build these agentic workflows, we need new infrastructure to connect these facilities specific to the attributes of agents. And really that's where I envision Academy fitting in. So when we talk about agentic middleware to a software layer that manages the lifecycle communication coordination of autonomous agents across distributed computing infrastructure, that's what we're targeting. That's what we're trying to build. This really comes with a scope of very difficult challenges. From the high level, which is I think where a lot of people start, is how do you integrate LLMs? How do you call them? How do you train them? How do you orchestrate multi-agent conversations between them to enhance reasoning, to equip them with tool calling and build protocols so that they can interoperate with each other and with tools built for other services such as MCP and things like that. But there's also all of these low-level challenges that from a workflows community, from a distributed systems point, we're very, yes, this is where LangChain, AutoGen, Identic AI start. But from low-level challenges, distributed systems, such as how do you deploy these agents, especially across research infrastructure? How do you make them tolerant of instruments going down, of maintenance schedules on HPC machines, things like that? How do you manage the data movement where LLMs deal with conversations that may get long? We deal with terabytes and exabytes of data produced by experiments. And how do you migrate and how do you move both the data, the agents, the facilities, et cetera? And that's where we're starting to approach this problem with Academy. And you really shouldn't be thinking of these things as alternatives. We want to design them such that they're complementary, and that we can meet in the middle and we can accomplish really cool science by combining Academy with all of the frontier labs, all of the industry techniques for building multi-agent systems. So why do we really think that we need new solutions for science? It's because we're trying to build agentic applications that go beyond multi-agent conversations with LLMs, right? So we do have this category of conversational assistance where we want to build a tool that you can ask, what is this chemical property? And your agent knows how to go run a simulation. But we will also want to do things like build multi-site applications where you can deploy an agent on your HPC machine and an agent on a different machine with more resources or with a CPU only cluster. And those agents know how to monitor the machine. They know how to allocate resources. They know how to request more work and decide what needs to be computed. We want to integrate self-driving labs and telescopes into these workflows tightly. So not just data gets transferred there, but we can control what's happening. We can decide what images need to be taken at a given night based off of what we've seen before. And then this also, like both of those things tie into, we want to steer workflows as they're happening. We want to adjust the tools we're using based off of the data that's coming in, or we want to decide which molecules we need to simulate as the environment changes, as the goal changes, or as we learn more about experimental results from the facility. So all of these applications can be thought of in an agentic manner that goes beyond LLM. So agents are really a way of building these workflows, and it's more than just querying a OpenAI API. And when we think about this, we start to see many different behaviors emerge that we need to support. So we have these monitor agents, things that will just watch what's happening and tell other agents about them. For example, on the file system, or perhaps monitoring the weather so that it interacts, so that we know when we need to retrain or reissue predictions, things like that. We have these low interactivity agents with high autonomy, things like optimizers that can reconstruct your workflow based off of what's happening, but don't take input or just given a goal. We have these service agents that have high interactivity, but low autonomy. And then at the other end, we have the LLM agents, which is, I think, what is most well supported. But in order to build effective scientific applications, we think we need to support all of these. And this is just one of a range of categories that we could be looking at. We could be looking at how long living they are, how general they are, if they're embodied or not, and how embodied they are, right? Are they just controlling a telescope, or are they able to synthesize dangerous chemicals, things like that? And really the vision here is that future scientific applications will need to incorporate all of these behaviors, and we need to design the primitives to support them without biasing the creation of these agents. So what this really boils down to is there are, or what the design philosophy of Academy really boils down to, is that this is trying to advocate for a different way of building these agentic systems. So what we typically have is we have a centralized approach. So all of these quote unquote agents are located on a centralized workstation, a cloud node. And in order to use any infrastructure, what's typically called tools are, they're available via APIs, via MCP servers, REST APIs, etc. And this has a rapidly growing library and ecosystem, but what we find is that it's actually really hard to get this to work on instruments that may not always have internet access, or labs where you need the controls, like self-driving labs where you need the control to be on the device, or HPC systems where policies prevent you from opening ports to serve an API. And this is where really, again, where LangChain and AutoGen and all of those lie. But what we're moving towards, what we think is a more powerful model, is this decentralized approach, where agents are actually distributed across the infrastructure. They can interact asynchronously when they're online, so they can be spatially decoupled as well as temporally decoupled. And that means they can use infrastructure directly. If they live on a robot, they can actuate that robot. If they live on the HPC cluster, they can watch the cluster, they can submit a job, they can cancel a job. And this really benefits things in terms of data locality, in terms of performance, in terms of coupling. But it does introduce this element of deployment complexity. And these are the issues and problems that we're tackling in the design of Academy. So how do we support both this diverse agent behaviors as well as the deployment and management across distributed federated resources? And we do that with a multi-tiered approach. So the first focus is we create a simple Pythonic interface in order to program and interact with agents. And I'll walk through this in a few slides, but agents are defined as a Python class with specific actions that can be invoked, as well as control loops, which give them autonomy. And these agents have handles, and these handles are, again, a term that we would borrow from the actor programming framework, but these handles allow agents to be invoked from other agents or from users. So you can use a handle references a remote agent, and the handle can be used to call the actions. And again, from the actor community, each of these agents has a state that determines what actions they can take and what actions they'll take next. And this state might be resilient to failures of the node or the systems going offline, et cetera. Then the second focus is how do we deploy these agents? So we interact or interoperate with existing solutions that have been widely tested and deployed, such as Ray, such as Parcel, such as Globus Compute, to deploy agents across distributed infrastructure. And then the third focus is coordinating the messaging between agents. So we build an asynchronous data plane that's decoupled from the control plane for agents to communicate. And this is built on the concept of mailboxes, which again, a very well-known concept from distributed systems and operating systems that gives us this temporal and spatial decoupling. And right now, you can deploy your own exchange to manage agents securely across your resources, but we also have an authenticated cloud service that you can freely use to manage communication between your agents. And like I said, for the launching and deploying agents, we've tested several solutions with Globus Compute to launch agents across different federated resources, or Parcel, which is a pure Python library to manage agents on an HPC cluster. So now I'll go into a little bit of what this programming model looks like to write apps in Academy. So this is an example agent. So an agent is a Python class that inherits from the base class. This defines a behavior that an agent will take. Each instance of a behavior can have its own state that will be instantiated as the agent is deployed. In order to define actions that other agents can invoke, you define an asynchronous method and you annotate it with this action decorator. This will make it available to any agent that has your handle and can communicate on the exchange. And then you can also program autonomous behavior using this app loop function. So that will be started when the agent is started up and can be shut down either manually through an action, or will be shut down when the agent dies or when the agent is purposely killed. And all of this example and stuff are available at the docs at academy.proxystore.dev, and I'll have all of those links and everything at the end. So once you have your agent, how do you manage and deploy it? So there is a single unified interface for managing agents via the manager class. That takes in your exchange, which in this case we're using the local exchange factory, and your executor. So here we're launching agents via Globus Compute. And again, this Globus Compute model allows you to turn any computing resource into a function as a service endpoint. So you just fill in that endpoint to create a Globus Compute executor and pass that executor into the manager class. To launch an agent, you can instantiate the agent and then call launch with the manager, and that returns a handle to allow you to interact with the agent. And then the remote communication looks like a function call where messages are asynchronously passed through the exchange to the agent performs the computation, and then puts a result back in the manager's mailbox, and shutdown can operate the same way. So this handle is portable, so it can be passed to other agents or other contexts. And this really allows the management of your agents. And again, so we're thinking of Academy not as an alternative to using other LLM providers or agent SDKs, but as a complement to it. So there's really this ability to turn Academy and to turn any agent into a tool that can be used by your conversational AI. So this is just an example of how you would do that. You can annotate a call to a handle with a tool function. Oh, shoot. With a tool function, and then pass that tool into, in this case, LangChain. And this is an alternative way to set up tools compared to MCP, which has become extremely powerful and popular, but it's often hard to manage and deploy on HPC resources, for example, where you where you can't open a port for inbound communication, or resources that may be on or offline, so the MCP server isn't always available. And then the other alternative that we've investigated or we've used in the past is this function as a service model, such as the Globus Compute. And this really is built for federated execution, so it's built to execute tasks on research infrastructure, but in contrast to Academy, these tasks must be stateless and short running because they are just functions. So really this Academy gives you the ability to deploy long running functions with state to federated resources, which we find important when building agentic workflows. Then another push of integration that we're working towards is provenance in agentic workflows. So this is with Flowcept, which is a lightweight monitoring and provenance tool. So with that, you can annotate different actions with a Flowcept decorator as well, and that allows you to capture agent-specific extensions to your typical provenance annotations. These are things like an AI agent attributes a decision to, or a decision is attributed to an AI agent, or data was attributed to an LLM call or used a certain prompt. And some of that can be seen in this figure, as well as the citation of the paper from Oak Ridge. And what this really lets you do is integrate, in addition to integration with Flowcept, is you can now leverage tools like Grafana to do monitoring. You can have an LLM interaction about your provenance graph, things like that. So I don't know where we are on time, but I think I will very quickly go through some of the use cases. I believe we're around 20 minutes, and this was supposed to be a 20-minute talk. So I think I'll just a specific use case that we've looked at is MOF discovery. So MOFs are these metal organic frameworks. If anyone was paying attention last week, this was the Nobel Prize winning discovery for chemistry this year, but they're really the sponges of science. So they can be used to do things like clean up oil spills or optimize them for capturing carbon from factories or other industrial settings. So this is just a diagram of the MOF showing the nodes and the ligands that are used to make the sponge. And really what's important here is that the space, like the possible MOF combinations, are intractable. So in order to design MOFs, you need a powerful computational search. So we built this application in MOFA, or we built this application called MOFA using autonomous agents. So those agents are distributed at different facilities. So we deploy a molecule that, or a model that generates potential ligands to the Aurora supercomputer that can scale using thousands of nodes. Excuse me, I'm sorry. Then we deploy another filtering step to optimize those generated ligands to the Polaris supercomputer that gets a different set of resources. And then we deploy several agents that do other forms of assembly or filtering and storage to cloud nodes. And at each of these places, the Academy agent manages its own resources, manages its own workload, and in a decentralized manner passes off valid or invalid MOFs to the next step. And really what this enables is that eventually this is a modular workflow, so eventually we hope that this can be integrated with, for example, a synthesizer agent that's equipped with a self-driving lab. So yeah, this is just some of the results of what you get from this. So because you have agents managing their own resources, they can scale out separately based off of how much work they have to do. They can manage the submission of jobs as wall times expire and things like that. You also have loose coupling so that you could swap agents and integrate new agents eventually. And then again, in the future, we hope that this gives you the ability to build workflows that share agents. So for example, multiple agents might need, or multiple workflows might need the ability to optimize the structure of a generated molecule, and they can all share the same agent. This is another use case, whereas in the MOFA use case, we had agents manage their own workflows. I think the interesting thing about so this is an astronomical spectroscopy use case. And just to breeze through it real quickly, I think the interesting thing here is this was an existing stateless workflow built with Parcel, but one of these agents one of the agents was estimating the optical parameters of the telescope used for this IFU spectroscopy, and this could be improved by giving that task state. So that task, those parameters are continuous in time, and if the task that was estimating those parameters could use the previous parameters and use those to learn the future, how to calibrate future images, we were able to improve both the resolution of the generated images and the speed in which they were processed. So yeah, sorry for going a little bit long, but this is a portion of the team at UChicago, some summer students that we work with, and then the team at Oak Ridge working on the provenance portion. I have several action items for you guys. Please go star the GitHub repo. Join the Slack channel. We have a Slack channel linked from the Academy-Agents website. That is a great place to engage with the community and get help as you follow the tutorial that we have on the GitHub to walk you through some examples of building agents with Academy. If you are there, we are also doing a more extensive version of the tutorial at SC in November. So please attend there, and we'll have some fun engagements. We'll build games. We'll have a battleship tournament. Please install and use Academy. Yeah, so thank you guys very much.